Here we've been given what is called a system of equations to solve. That's where we have two or more equations and we're looking for the place where all of the equations would be true, where they're going to overlap. Now notice that this one we've been asked to do it graphically, so we're going to draw a picture of these two lines that we have. They are both lines that are in standard form since our degree, our highest exponent, is a 1. Now, since we've got standard form, the easiest way for us to draw it is usually to find the two intercepts. So let's see if we can do that for the first line, x plus y equals 3. If I'm going to find a y-intercept, the way I do it is I put 0 in for x. So this is going to be gone, and you end up with y equals 3. So the y-intercept is 0, 3 for this particular line. Now we can do the same thing to get the x-intercept. Let's put 0 in for y. That makes the y go away. We would end up with just x equals 3. So 3, 0 is the x-intercept. Now, once I know those two intercepts, well, then I can just plot them on a coordinate plane and draw the picture of it. Here is our y-intercept, 0, 3. And then here is our x-intercept, 3, 0. Now, remember what this line means. What the picture means is here are all of the solutions for that equation that we were just looking at. Anything that solves the equation shows up on this line. All right, let's go back and look then at the next equation, x minus y equals 1. When we try to find the intercepts for it, a little bit harder, but not bad. If I put 0 in for the x, this x is going to be gone. You've got minus y equals 1. Now, we don't want minus y. Let's solve that for y, dividing everything by -1. When we do that, we would get y equals -1. So when x is 0, y is -1, and that gives me a y-intercept of 0, -1. Let's do the x-intercept. Putting 0 in for y, x equals 1. So 1, 0 is the x-intercept. And here we'll draw that picture. And anything that is a solution to the equation we were just looking at now shows up on this red line. You can see 0, -1 and 1, 0, our two intercepts that we found. So now we said that anything that is on the blue line was a solution to the first equation. Anything that is on the red line is a solution to the second equation. So what could we say about this spot where the 2 points overlap? That's right. It's a solution for both of the equations. Now, that point where the two places are overlapping, the ordered pair that matches up with it, it's 2, 1. The x value is 2. The y value is 1. If we look at our original equations, let's see if 2, 1 would work in both of the original equations. 2 for x, 1 for y, 2 plus 1, that's 3. 2 for x, 1 for y, 2 minus 1, that's 1. So it did indeed work in both of the equations. The solution to a system of equations is the point where the two lines are overlapping. So we should express our answer with both an x and a y and as an ordered pair. Now, once we've done that, there are a couple of things that we'll want to use as words to describe our systems of equations. Anytime that you draw the picture and you actually see two distinct lines, we call this an independent line. The two lines are independent of each other. When you only see one line, then you would call it dependent instead. So 2 lines, independent. 1 line, dependent. Now, as far as our system is concerned, the words that we use to describe it, if they cross the 2 lines, if they cross at one point, we say that the system is consistent. C for cross and C for consistent. When they cross at one point, it is a consistent system. If they cross in every point so that you just had one line that you could see, then it's still crossing, so you still say that it is consistent. C for cross, C for consistent. If they have met in one place or in every place, then we say that it is consistent. If they didn't meet at all, if we had parallel lines, then there is no solution to the system of equations, and we would say that the system is inconsistent. Parallel lines, they don't meet. The place that they would meet would be the solution to a system of equations. Since they don't meet, we say there is no solution and they are inconsistent. Now, with these that crossed in every spot, they have an infinite number of solutions because anything that's true for one would also be true for the other. So when you see two lines, you say independent. If they crossed, then you say consistent. If they don't, you say inconsistent. If you see only one line, then you say dependent. And with one line, it is consistent. So we've seen how a system of equations can be solved graphically, and we've learned that the intersection of the two lines, this point, is the solution to the system of equations. Now this one worked out nicely because the x value is easy to determine, that's a 2. The y value is easy to determine, that's a 1. So it was easy to tell what our solution should be graphically. What if the answer was supposed to be a fraction, though? What if it was a little bit harder for us to read what our solution was? We need a better way to be able to find the solution to a system of equations that doesn't depend on our ability to draw. One other way for us to solve a system of equations using algebraic techniques instead of graphical techniques is called the substitution method. Let's look at the exact same system of equations, x plus y equals 3 and x minus y equals 1. And let's work this problem again, but this time with the substitution method. Now we should get the same solution, 2, 1, by the substitution method that we did doing it graphically. For substitution, we're going to take one of the equations, doesn't matter which one, and we're going to solve it for one of the variables, doesn't matter which one. Usually, the best thing for you to do is to make as many things positive as you possibly can. That usually gives you better arithmetic later on as you continue to work the problem. So knowing that, I'm going to take the bottom equation and I'm going to solve it for x. So notice we've left the top equation alone, but the bottom equation, when we solve it for x, that means that I'll move the y to the other side to get the x by itself. That gives me x equals y plus 1. Now, what this means, anywhere in this problem that I see an x, I can now replace it with what that means, which is y plus 1. So we can take the y plus 1 that we know x to be, and we can substitute it into the other equation in the place of x. Let's do that now. Anywhere there's an x, let's replace it with y plus 1. Putting y plus 1 in for the x gives me y plus 1 plus y equals 3. Now, I didn't really need the parentheses there, so let's take those away. Adding together the like terms, y plus y made 2y, and let's bring down that plus 1. Now, this is an easy enough equation for us to solve. Subtract 1 from each side, divide by 2, and now you know that y is equal to 1. But the solution to a system of equations is the point where the two lines are intersecting. So I've not completed this by just knowing y. I've still now got to figure out what the corresponding x is. So let's see if we can figure out what x is by going back to where we had solved for x before, put the 1 that we just found in the place of y. 1 plus 1 is 2. So our solution is 2, 1 again. Remember, since it's two lines that have crossed in one point, we say that our solution is independent and consistent. The third method for solving a system of equations is called the elimination method by most people. Some people call it the addition method. Let's take the exact same system of equations, x plus y equals 3 and x minus y equals 1, and this time let's solve it using the elimination method. We should still get the solution 2, 1. To solve using the elimination method, we need completely opposite coefficients on one of the variables. Now for this problem, notice that the y's in red are already opposite. So really this one's set up for us to start very easily. Once we've got those opposite coefficients, what we'll do is to add the two lines together. This is why some people call it the addition method. Now, when I add the two lines together, x plus x makes 2x. The y's are going to add out, or they are eliminated. This is why some people call it the elimination method. So now 2x equals 4 is all that's left once we add the two lines together. That's easy enough to solve. We know dividing by 2 that x is going to equal 2. Now remember, we aren't done until we know both the x and the y value, and we write our answer as an ordered pair. We can go to either of the original equations and figure out what y is now that we know x. Remember, x is 2. Let's go to that top equation, and where there was an x, let's put 2 in its place. 2 plus some number is 3. That number had to be 1. And so again, our solution is 2, 1 as an ordered pair. The x value first, the y value second. Now this one was a little bit easier than some of the problems will be because we already had these opposite coefficients to begin the problem. If you don't already have opposite coefficients, you can create them by multiplying one of the lines or maybe both of the lines by any non-zero number that you want. Can't multiply by 0, that would make the row go away. But we can multiply any of the rows by any non-zero number that we like to create opposite coefficients. We'll see one of those a little later.